Today is kind of the last of the traditional lectures. So objective today is to see how generators are a more general kind of iterator. So recall iterators from last week. Well, this is not last time. Last time we did the user-defined classes. Objects, and then today we'll recap. Oops. Oh, let's just do. We'll recap of the counter iterator class that you're seeing for your assignment, and then counter re-implemented as a generator, and then diving into how CPython, which is the interpreter, name of the interpreter, to implements generators. Okay, cool. So so this is still due Friday. So this is interesting because this is the last, like I mentioned, this is the last of the Python deep dive lectures. And this is really neat because I've actually never seen a class go over kind of a language interpreter in detail like we have in the past 6 weeks. So really, I mean, I'm pretty confident saying that after you get through this week, you'll be you'll be amongst the people in the world who know the most about language interpreters, and especially about the Python interpreter. If you actually try to look online for documentation about this, as some of you probably tried, there's nothing. Because nobody actually knows this stuff except for the people who wrote the code. There's a few blog posts I found about people trying to write up stuff, but I think that I'm pretty excited for kind of what you're going to do throughout the class, because already a lot of the stuff that you all wrote up for the annotations, and then hopefully the midterm writing, that's actually that will increase the amount of, if we actually release all this, this will be, this will add to the sum body of knowledge about the Python interpreter by tenfold, because really no one has written about this in an organized way, which is shocking because Python is used in so many places, right? It's one of the most commonly used languages in the world, but no one actually knows how the internals work except for the developers. And I think it's a really fascinating case study because, as you've seen, the Python code is actually, for being C code, is relatively straightforward as far as interpreters go. Because other interpreters for languages like Java, like the stuff that's running your browser, these JavaScript interpreters are actually really sophisticated because they try to run very fast. And one of the design things with Python is that the designers didn't necessarily care about it running really, really fast. They just wanted the code to be really clean. And for a code base being this code base is probably 15 to 20 years old, it stayed relatively sharp and clean, which is extremely rare, because if you actually look at any code that's 20 years old, it's got tons of weird things in it. So we'll kind of conclude our tour today with generators, which is a really different thing that I've never seen this in other languages. It might appear in some more obscure functional languages, but definitely not in a mainstream program. So who has heard of generators before in Python? A little bit? What have you heard about it? No.
I did some. When you do classes, you have to iterate over it, but it's different from iterators.
Yeah. And
I can't say exactly why, but it's something like custom iterators.
Right. Good. So I think you basically got the gist of it. Is that iterators are this interface we define where you have this this next method and a stop iteration, and you can use generators to write iterators. I think that's the only thing I'll go over in this class. That you can use the generators to write iterators more easily, but you can also use generators for all sorts of weird stuff that's more advanced that we won't go over. So the way to start is we're actually just going to go to the code example from the assignment. I think it's count. Yeah, let's do this one. So this is the count. Well, actually, let's just download it from the website just so we can have a clear copy. So assignments, I'm just gonna copy and paste just so we have the exact same one. So this one, 5.7. Okay, let's just do 5.7. So I'll copy this and paste it in. I'll call this it.py. I mean, it's almost the same. So I'll call it.py and paste the code. Okay, so if I run this, it's not a surprise that let's open a new terminal. If I run this Python it.py, it prints out 5, 6, 7. So I guess this counter is inclusive, right? It goes 5, 6, 7, and then it stops. So let me get the light. Can people see in the back when the light's on, even? Okay, so I'll leave the lights on. I think you can see. It's inclusive, so it goes up until it stops. And basically the trick to this is the iter returns itself, which is okay because it's just, it just needs to return something with a next method. And it just happens to be itself. You can imagine returning another object, but it's just itself. And the next method is, it increments it by 1 and then returns the previous value. And then if it's greater than this, it stops. Yep.
Is it just name matching for the next? So if you have just next and then do something that is really silly.
Yeah, it's just called next. Yeah, it's just a name. Yeah, I think it. Yeah. Did we go over that in the code on last week of how it finds the next name? Well, actually, maybe that might just make part of your assignment. Yeah. so yeah, I think you have to find where it goes next. Yeah, but it's the name next. I think the iterator interface is next. Yeah, it's a protocol. So next. Oops. Yeah, iterator.next right here. There's the iterator protocol right here. So this is a Python documentation. Iterator objects must support 2 methods: iterator object itself, and then .next. And so if no further items, raise to stop iteration.
But we don't have the iter itself.
Yeah, so there's the iter method, __ iter, for our counter. It returns itself.
Oh, yeah.
So it just needs to return an object that has a next method. Cool. So then if you run it, it just goes 5, 6, 7. Okay, so conceptually what this is that it's a way of doing some count or something, right? So it's kind of a roundabout way to count. So what we're going to do in this class is to re-implement this whole counter thing as using a feature called a generator, which I think is a lot more elegant. And then we can actually write the exact same code. So I'm actually just going to comment out the code and just write it underneath. So a multi-line comment in Python is just 3 quotes. I just do 3 single quotes. That actually just makes it into a big string, but that's just a hack for commenting. 3 single quotes just makes the whole thing into a string, but you're not assigning. You can say like x equals that. You're assigning a string. You're not actually assigning the string to anything, so it just treats it as a comment. I don't actually know if it compiles in the bytecode. It might, which would be silly. But I'm going to comment this out. So if I comment this out, obviously if I run it, it dies because there's no counter anymore. So now we're actually going to define a counter. So to define a generator is simply a function. So we just say def counter, and then we what do we take? Low, high, because we want to match the interface of this, right? This counter you create with low, high, and then what we're going to do is we're going to set current, a local variable current, to low, and we don't need the high actually because we already have the local variable. So when we call this function, we're creating we're calling it with low, high as 2 parameters. Sorry, let me to get the color right. So now we first set current to low. And then what we conceptually want to do is we want to keep generating a number until it gets to high, right? So the code we want to write, I'm going to be off by 1. I'm going to check my cheat sheet to make sure I'm not off by 1. But it's really easy to get off by 1 on these because you don't do greater than less than, but it's not a giant deal. Let me just look at my sheet. It is... So while current less than or equal to high, colon, okay, ready? Okay, so while current is less than or equal to high, yield current plus equals 1. Okay, so that's it. So this yield is this magical special keyword in Python. And basically, if you define a function, def defines a function, right? If you define a function and that function anywhere inside has the word yield, Python will compile this function into a generator function, the special generator function. And that's actually it. Like this is the code. Like this is the exact same counter as all of this. I mean, this is not a ton of code, but like it's sort of indirect, right? You're creating an object, setting some local variables, you're using some underscore iterator return self, and then this weird next does an incrementing, and then it tries to check if it's greater than some limit, and then it raises an exception. So it kind of uses this exception to raise. But I personally feel this code is a lot more elegant, and I'll explain what the yield does in a minute. But basically, what conceptually this does is it. I'm really hoping I'm not off by 1. Let me actually test it to make sure I'm not off by 1. Good, 5, 6, 7. Okay, runs the exact same way. Okay, so I'll explain what this does now. So what this generator does is, first of all, you call it like a function, right? So when you call counter 5, 7, it's like a function call, and it creates a generator object in the C. It's called a generator object. And now you just do for elt in C, print elt, just like this is the exact same code that's using the generator and iterator. Right? Like I didn't, there was no magic trick. This whole thing was the exact same code, right? I didn't change the client code at all. I just changed the definition of counter to be much more compact. So conceptually what happens is when you call the for loop on the generator object, it'll actually start executing it one step at a time. And every time you execute, every time you call this function, it will go through the function and then it will yield the value. So normally when a function returns, yield is sort of like a return, but normally when a function returns, you're done, right? The function is popped off the stack, the frame is off the stack, you're gone. But the interesting about generators, after you yield, the function stays on the stack. And then you can actually call it again. And when you call it again, the execution resumes right after you yield. So basically the first time you call this function, the first time you call it, it goes like this, I guess. It goes current equals low, current is less than or equal to high, and then yield current. So the first time you call it, what is that? Low is 5, high is 7. So it'll set current to 5. Current is less than high, that's good, right? Then it'll yield current, which means it will actually return 5 to its caller. So that's why the first time you call this for elt in C, elt will actually be 5 because it's returned. And then you can print elt, which is print 5, right? Now here's the trick. The trick is the second time through this loop, you're going to go back and it's going to ask for C again. It's going to call this thing again. And now the generator remembers that the last line I executed was right here, the yield. And then it just keeps on going. So this is pretty bizarre because functions can't do that, right? Function, when it returns, it's gone. So it keeps on going. It remembers that the current value was 5, and then just sets current to +1, which is 6 now. And current is 6, and then just goes back up to the while loop. It's still less than high, great. Then it yields current. It just spits out 6 to the caller. Elt is now 6, and then we print 6. And then it goes again, and then it follows again. Current plus equals 1 to 7. Goes back to the while loop. We're still good, because high is 7. It yields 7, spits out 7 to the caller. And then the caller uses it, prints out 7. And then it goes back again. And now we're down here. Current is now 8. When we go back up the while loop, this is false now. We're done. And it drops out of the while loop, and it just returns from the function, right? And now this is actually a real return, right? We're done with the function. And when we're done with the function, the for loop actually stops. So that's sort of like the equivalent of the stop iteration thing. So a really cool thing about this is that the way to think about generators is that just anytime you want to write a function that you want to return something and then just keep going, you basically made a generator. And the most natural use for generators, I feel, in the beginning, is to make an iterator like this. So I don't have a compelling real-world example right now, but in the course of doing my work, I have examples where I use generators. Yes?
So, I was kind of fuzzy. So when you say goes into the generator, the code executes right before the yield, or it kind of just uses the entire while block? Like how does it know? How does it know like where
There's a counter. I mean, there's an instruction counter inside the generator object, right? To know where the last instruction
Oh, like
generated.
how does it know like where to put the instruction counter at? Like what will be counted as the beginning of the
generator?
The place that the second time you enter it, you just.
It's the line after the yield. It's the instruction after the yield is where you continue.
Oh.
Where you resume. So you yield and then you continue as though, as though you finish. Let me illustrate this in the visualizer, and let's see if it's more.
So it's more like you're. Okay.
Let's see if it's more clear here. But we should re-ask the question if this isn't clear enough. The visualizer doesn't do very well with generators, but let's see if it works. Let's see. Okay, so here. Okay, so zoom in and then forward. So counter is actually a function. So this is interesting because counter itself is a function, right? Because it's actually a function that, so I sort of always was not precise. Like the counter is still a function. Even though there's yield in it, it's still a function itself. But when you call counter, it will return a generator object. So when you call a function normally, a normal function, it returns you the return value. When you call a function with a yield in it, it doesn't return you a value, it returns you a generator object that you can then iterate over. So when you hit next, so now C is this generator object thing. And then you can actually do for else and C, which will iterate. So the first time you go, notice how low is 5, high is 7. And then now watch where the arrow is. Current is low, is less than high, and now we're going to yield current. So when we yield current is 5. We're just going to yield it back to the caller, and we're going to store that in elt. So let's do that. Return 5, and then we're back out, and elt is now 5, which is the thing that you assign to in the for loop. Okay, and now elt is 5. We can do whatever we want with it. We can print it. Good. Oh, so the printout shows down here. And it's kind of out of the way, but it prints 5. Okay, now we're going to go back in the for loop again in this red line. And when we go back in the for loop again, notice how the execution resumes. The frame is still there. Low is 5, high is 7, and current is 5 now. And notice how the line is here now, and we're just going to go right to the next line. Right, current plus equals 1, current is 6. We're going up here, and then we're going to yield again. Pops back out. Elt is 6, and then it prints it, and then it prints it here, and then we're going to go back in. Current is 6, and then we're going to just keep going. It's 7, and return it. Elt is 7, and then the final round is now it's 8, and then this is going to fall off and break, and it's just going to get out of the function, and then we're done. So that is the control flow for generators. So the basic idea is that when this function is called again and again, it resumes where it left off. It resumes at that yield where it left off, and it keeps all of its if you notice, it keeps all of its local variables, right? All the local variables get maintain their values. It's not like they were lost, right? So each time current, low, high is keeping the value. So the generator maintains its state even across different calls. I mean, it seems like an object, right? Like when we had the counter when we defined the counter as an object, this is very straightforward how it keeps its state. It keeps its state because it's an actual object. But the generator actually is an object as well, and it keeps its state in the local variables, namely the parameters, low and high, and the current local variable. That's all local state stored in the frame of the function. So it sort of acts like a very compact object that can remember its state and keep going. So a common generator in the standard library is the OS library, Python OS walk. So then I asked, what are uses for generators? So this actually occurs a lot in standard library. So os.walk is a function in the Python standard library that takes a directory root directory, and then it starts generating subdirectories from it and files from it. So then what it does is what you can do is you can say for directory in os.walk, and it'll do a for loop, and then you can do something with each directory. So it's sort of like you can write a recursive function that traverses all the directories and like checks how many files there are or whatever. And this is nice because the nice thing about having this as a generator is that it saves memory, right? Like let's say you had a billion directories in your hard drive. os.walk actually just traverses your hard drive, grabs the directory name, yields it to you, you use it, then it goes, resumes execution, goes to the next directory, yields the name to you, and says, yes.
Can you only have one yield in the body?
Good question. So what do people think? You have one yield or more? Could you have more than one return in a function?
You can have more.
Yeah, you can have more than one return in a
But
function.
then the case is you might use the upper yield ones, and the next time
It will go to the next yield. Yeah. So that's why people have weird use for iterators. Yeah, generators. So you can't have multiple yields. So it will just do what you think. It will, have a yield up here and yield down here. It will yield, and then it resumes executing, and it will do that second yield, and then it goes and loops back to the first yield. And
so to that generator's knowledge, it doesn't really care like which yield it executes. It just kind of is a pack of bunch of codes, and then you can use kind of different initial kind of settings.
Yeah.
And then do the computations at different yields.
Yep. Okay. So you can do multiple yields.
Yeah, the behavior is completely different
Pretty
when you call it. It could be each time you call
That's
it.
why it's crazy.
Again. Yeah.
Yeah. So you can multiple yields, and the other thing which we won't cover because I don't fully understand it.
Pretty much like you're aware of some sort of context, and then
it's like a function that saves its context.
Oh, pretty awesome.
So it's pretty awesome. So the other thing you can do generators is that you can, when it yields a value, you can actually send a value back into it. So when it resumes, it's like you throw another parameter kind of into it, and it's really weird. So you can actually, the generators can be used to communicate both ways.
So you can throw the generator away, like you can pass it.
You can pass it stuff,
You can pass it in between. Okay.
Yeah. So then what you can imagine is you set up multiple generators that pass stuff between them, and everything explodes. Like it's crazy. So the way we've been using generators is one yield, it just spits out stuff to you, and then you do a for loop over it so that each time the for loop happens, it yields. So one of the other use for generators, you can actually do generator yield from, I think, something like that. Oh yeah. Well, hey, this is a great thing exploring your project. So this is a great project idea. If you're really interested in generators to explore them, there's a thing called code routines and stuff. So yeah, I think this is an awesome project if you're interested in exploring this more in terms of projects, like more advanced features. I think that'll be really, really fun. But we won't cover them now. So the main thing with generators is the fact that they save memory because it only yields you one thing at a time. So the walking directory tree is an example. Another example is like a log file. So this is a interesting example. So imagine you wrote a generator to imagine you had a lot of you probably parse data like log files. You read a line at a time in like a server log or a CSV or data file. Then you split that line by some delimiters, and then you grab some of the fields out, you make an object, you maybe clean stuff up or check stuff, and then you give an object to some other piece of code processing. So the naive way to do this is to read all of your stuff at once and generate a giant list of objects, right? So that's fine if your data isn't big, but if your data is Google size, you have trillions of petabytes of log files, you can't just give someone a list of, you can't take a terabyte file and give someone a list of a billion or trillion Java objects or whatever. It would never work, especially if they don't need all billion at once, if they're just processing one of them. So instead, you can write a generator to go through your file, and every time you see a line, you actually run some code to parse it, and then you just yield the result. And then when you go to the next line, you just yield the next object. So then whoever consumes it can actually process your thing one record at a time. It only takes up enough memory for one record. So that's actually a very efficient way to process data. And it's actually really elegant in terms of code. Huh? Yeah, so actually let's just write this as an exercise. Because we can go into internals also, but this is not going to be on your assignment. So this is more just enrichment. Let's do a data processing one since we're so our data is like, I don't know, names.dat or something. I'm just going to make up some data format. Okay, so, we can say first name equals something like that. Okay, so I'm gonna run out of names here. We should actually grab some real data somewhere, but let's just do this. Okay, so as we have a few rows of data, right? So imagine you have data like this, and it's like a billion rows or something. Yeah. So imagine I wrote code. I want to write code to like process this data, right? To like do something useful with it. So the first thing to do when you're writing code is you want to read every line and parse it. So I'm just gonna parse.py. This is I actually wrote code somewhere else. Let's call it process.py. So for line in names.dat, I think this is the data file. Okay. So this is just a Python way of parsing. So line equals line.strip. This strips the end of the line off, and then print line. I just want to print it just to as a sanity check. This just prints the line. And this is just an illustration of generator, since you mentioned it. So process. So what do I do around there?
You should open.
Good. Yeah, I didn't open the file. I actually are iterating over the string names. Okay, so just open, and there we go. Okay, so this actually goes through one line at a time. Actually, this is a really meta point. When you do file open, when you do for line open, that's actually a generator that generates one line at a time. So it actually spits you one line back at a time. So the open will give you a file handle, and it actually, when you say for and open, it actually goes one line at a time. So that's why when you say for line and open something, it's actually very space efficient, because it doesn't read the whole file memory at once. It starts reading it. It tells the OS to read it one line at a time. So if you're familiar with how file systems work, it basically there's a file pointer saying this is the beginning of the file, and then when you call for line in something, it will advance the seek pointer, the seek head, to the first new line character and just give you that line, and then when you call for line again, it'll go to the next new line character, next character. So it never actually fills up your RAM with the whole file's contents. So it's actually very memory efficient. Okay, so what we actually want to do is we want to process this line. So the first thing we do is we say something equals line.strip, split by colon. So first, I'll just say fields equals that. So if I print fields, we actually get a list of two things. So split by colon actually, comma, splits the thing at the comma. So if you remember what the data is, there's a comma. And now we have something equals something, something equals something. So I mean, again, we could write more complicated code for this. I'm just doing a super simple code. So we can say first name equals, okay, so field 0. And then last name equals field 1. So if we now print first name and last name, we should get the two sides of the comma, right? But then we actually, they're stuck on, right? We need to get the thing after the equal sign. So the way to do that is we split again by equals. We split each one by equals, and I'll show you what this is. Oops. So just not confuse it yourselves. Let's print them on separate lines, and then we'll print an extra line between. So I'm printing the first name thing split by equals and the split. And so split just basically turns a string into a list of things split by things. So if I do that, I get first name Philip, last name that, first name that, last name that, whatever. So I just need to grab this part out. I don't care about the thing that this is the first name. So a good sanity check actually is, well actually I just do 1. So 1 is the second element of the list. So if I print this, it should get that, right? Those are the things. So normally when you build up these data analysis scripts, a good suggestion is to start with a small piece of data and then build up your script before you run on the whole, giant Google size data set. So we have this, and what we really want though is we could write all of our analysis code in here, right? So write all of our fancy analysis code in here, right? We could do that, that's fine. So then we just have a bunch of code in there. But the kind of annoying thing is, imagine if this is really complicated, right? Parsing is not that complicated. But imagine if each record or line was really complicated to parse. It would take 100 lines of code to do error checking and to do different splitting and regular expressions and just weird stuff. It's strange to have, this is parsing code and analysis code. It's very strange. I mean, it feels unclean to have parsing code mixed with analysis code, because the reason why they're mixed is because we are stepping through this file and we have to smush the two together because we want to have a memory efficient thing, right? We want to have all of our parsing code and analysis code. We need it together, right? But so with the concept of generators that I'll show you throughout this class, then we can actually separate out those two very nicely. So let's just do some analysis first. So let's, I don't know, our analysis code is, let's just print your name in some reverse order. So let's just say, actually, so we'll say fn equals this and ln equals this. So that's the first name, last name. And then so our analysis code is print last name plus comma plus first name. Okay, so we're not doing any fancy analysis, but let's say our analysis is like 100 lines long. So we do this, we're actually going to just print people's names back and, you know, some kind of order we put in a spreadsheet. So, you know, that's that, right? So, you know, the thing is, imagine again, use your imagination, this is giant. So the interface between this is two variables, fn and ln, right? We really are parsing the data file to get these two thingies out, and then we want to do something with it. So one way we can separate this is just to build up a list and just pass it in. So list equals empty list, and then we'll just say list.append a tuple of first name and last name. Remember, the parentheses makes a tuple. So this is just a list of tuples. And now somewhere else for elt in list, first name equals elt 0, last name equals elt 1, and print last name, first name. So this should do the exact same thing. Let me just check. Okay, it does the same thing. Okay, so I just want to recap what I just did. What I just did is I created a list, and then I appended all the data I parsed into the list. So if I print list first, I'm just going to show you the whole list. Okay, so this list is all of my data, right? This list is all of my parsed data. The first line is my first name, last name in a tuple, then Bob Smith, then Jane Doe, then Carol Chen. Right, this whole list contains all of the parsed data. And recall that my original data was this, right? This is the raw log file, and I parsed it magically into this list, which is great because now we have a list and we can iterate over a list. We can write a for loop, analysis code. So let's say I wrote this code and I passed it off to my friend. And my friend and colleague is the data scientist, and she's writing the analysis for it. And all she wants is a list of tuples, first name, last name, pairs, so that she can do whatever analysis she wants. She wants to print them, she wants to look them in the database, she wants to visualize them, whatever. So all she cares about, if you notice, her analysis code is just for elt and list, do something. Tear the two things apart and do something. So what's the problem with having all this in a list that I alluded to earlier?
It's all there.
It's too large.
Yeah.
If the data size is too large,
That's right.
You don't want
The list is proportional to the data size. So if my input file is very small now, it's only 4 things, that's great. But if my input file is 4 trillion rows of text, this code actually goes through all 4 trillion whatever rows and appends 4 trillion things onto my list. And that will probably overflow my memory, and I can't actually run this. So there's two problems with this. One is the space issue of I'm going to overflow my memory, so this will never finish. The second one is a time issue, right? That even if I had infinite memory or a lot of memory, I have to wait for this whole stupid thing to finish running before I do any analysis, which is also pretty much a bottleneck. So if this code took, 10 hours to run, then I have to wait 10 hours, need to wait 10 hours before I start running the analysis code. Okay, so, but this will work. I mean, this works, and but we just want to optimize it. So the generators are purely an optimization in this case. So in this case, what we do is, let's actually define a function. So let's, I'm going to refactor this in the function. So define get parsed names. Okay, so let me, sorry, I indented wrong. Okay, so what did I do here? I want to just step out. I just made this in a function, nothing fancy. I just indented everything. What this, let me get a local variable. Okay, so list is a local variable. I just go through the file and I return the list in the end. Then what I do here is to use it. This is basically, okay, so this is, I'm the parser, right? Parser function. I wrote this as a parser. And my interface is I'm going to give you back a list. So if you actually want to make this a little more general, file name. If you want to make this a little more general to make it look nicer, just take a file name in. So you can parse any file name, so not just names.dat. So this is a parser function. This says that if you call me with a file name, I will start parsing your file and just give you back the whole list in the end. So to use this, I say for elt in get parse names. Get parse names, what is it? Names.dat. So does that code make sense? Get parse names just gives me a list. It literally gives me giant lists, and I iterate through it. So let me make sure I didn't make a typo and it works. Okay? This code still works. The refactored code, what it does is that it calls this function. This function parses everything, appends first name, last name tuples to the list, and then we grab this for elt and parse items, and we print out or do analysis. Make sense? Okay. So now for the generator part, let's actually rewrite this code as a generator. If we rewrite this code as a generator, we do not have to modify the analysis code at all. The user, if you notice how this is just a for loop, it just happens that this is a list, and a list can be iterated over the for loop. But remember that a generator can also be iterated over with a for loop. If this returns that's a generator, we can just keep calling for elt and generator, and it will do the exact same thing. So do people have ideas or suggestions about how to make this code? Oops, let's fit it all on one screen. Can we fit it on one screen? Yeah. Can we see that? Okay, let me make it a little smaller so we can fit on one screen. So anybody have suggestions on how to turn this code into a generator?
Get rid of return and then change the list append to yield.
Change the list append to yield. Yield what? The tuple? Okay.
And then get rid of the return.
Get rid of the return. Like that.
Yeah, that's right.
What do you think? Yeah, so I'm hoping that's right. Yeah, I think that's right. So let's actually run it to see. Exact same thing.
Yay.
So notice how we didn't change the code at all. All we changed the code did is instead of, well, we'll just show you the trick one more time. Instead of creating a list, appending to the list, and then returning the list, all we did is we just yielded the first name, last name tuple, and we can actually get rid of this list now, right?
Yeah.
There's no list anymore. And it's the exact same code, except this is actually simplified, right? This version of the code is actually simpler, because all this conceptually says is when you call this function on a file name, first I'll open the file, start going through the lines, yield this, spit it back, and then when you, right, so when you start executing, go here, open your file, do all the parsing, yield, which spits back, what is it, like my first pair? And then when you call it again in the for loop. Hey, we're here. Let's just go back up to the for loop. And then let's continue. And we remember everything. We remember where we were in the file, remember everything. Yield again, and we just go again. Yes?
But there's an issue, right?
Uh-huh.
If you have another thread that is calling the same thing, but none of them gets the complete data, right?
If you have another thread. So the simple answer to this is the Python interpreter is single-threaded.
Oh.
So you can't actually have multiple threads doing this.
But you have two multiple processors and reading the same data file? Is that going to happen?
Two multiple processors, right? The same.
Like the same file in the operating.
Oh, the same file. Yeah. Oh, well, then you have the same problem in other.
Okay.
No. Actually, it's the same. It's fine because when you open a file,
Oh, so that guy gets another copy.
it's another file pointer, right?
Okay, got it.
Yeah. So you have a file. Open gives you a file pointer. Somebody else can open the file too and walk
but
through it.
okay.
I mean, this is not a Python issue. This is just an OS issue, right?
Right.
The OS can have multiple readers to a file. Yeah, if you're reading the file and someone destroys it, then weird stuff might happen, right? But that's the operating system's problem to deal with. Okay, so questions about this code here, this generator code. So this is actually extremely elegant in my view because the cool thing about this parser function is it actually does what you see it doing, right? It actually just yields and just pops back up top and just keeps on going, and it completely works. And the advantage of this is that there's two full advantages. Right? The advantage of this is one, it doesn't take up any extra space. Every time this function runs, all it does is it just gives you a tuple fnln. It doesn't ever build up a full list of tuples. So that's one advantage. The second advantage is a time advantage. When you run it, you get the first result, and then, hey, look, you get to actually process the first result right away, do something, and then you ask for the second result. And then you get the second result, and you do something, and you get the third result, and you get the third result back. So you don't actually have to wait for everything to finish before you get to the analysis. So for those of you who are actually familiar with, so who's familiar with like these pipelines in Unix or Linux? So you've seen the pipe character, right? This is exactly the same principle. So the pipe character in Linux or Unix does this exact same thing except on a line level in the operating system. So when you're imagining, if you run a program and that starts spitting out data to the terminal to standard out, you can pipe it into another program, and that other program will start taking that data and consuming the data as soon as the data is produced, and then start using it. And then you can pipe it to another program and such. So generators used in this design pattern is like a pipeline interface. So you can imagine chaining these up in a pipeline. So if someone wants to do projects with crazy generators, that'd be great. Okay, cool. So I'm glad we did this example. So that's the example. Right? So imagine if I had 5 trillion lines, it won't actually slow down. I wonder if we can actually make this noticeably slower. I don't think we can, because our data is pretty small. Copy. How do I make the file bigger? Oops. Can I do that? Right? I can do that, right?
Yeah.
Does that work? Oh, no. It doesn't work.
Like you should have concatenating these two redirections, right?
Oh, I just clobbered it. Okay, great. I just deleted it. Oh, whatever. I just delivered the file. Whatever.
Inside the bin, you can
Copy paste.
and,
Yeah, we can do that. Let's see if this actually works. So, I don't know why we're doing this, but let's see. Let's make sure this runs. I mean, this isn't going to be on your assignment anyway, so we'll just have fun with this. Yeah,
You can type numbers,
type
like
the
1,000
number
and
and-
Oh.
1,000 ppm.
Oh, nice. Okay, so you do YY 1000p? Wow, that worked. Wow,
Yeah. Keep going.
100,000p.
And you can use dot to repeat the operation.
Oh my god. Okay.
Just keep dot.
All right. Let's see how big this file is. I'm trying to save it. It doesn't even save. Oops. Is that a gigabyte? No, it's only 127 megs. Is it? It's not even that big. Right, it's 127. Okay, let's try to repeat some more. Wait, I can just
Can
cat
you
this
use
now.
-LH.
LH.
LH, it shows you that. in readable.
Ah, what is it? Names.dat?
Yeah.
Okay, it's not big enough. So let's do copy names. Wait. Do I have a broken line in the end? Hold on. I just want to make sure I don't have a broken. It's like completely useless, but let's try it anyways. Wait. Oh, it's copy. Did I break the file again? That'd be so sad. No, copy did the right thing. Okay. So now we're gonna cat these. 3. Now it's getting bigger. It's good. All right, let's do one more, and then we'll see. I don't even know if the Windows file system can handle it this big. I don't think the Windows file system handled it. Because this is still Windows, remember?
Why not? Like NT.
Oh, maybe NTFS
NTFS
does.
could do it.
Okay, so let's. Oh, I didn't even get it that big. All right, names 4. Okay, whatever. Let's go to names 4. So let's do names 4.dat. Let's make sure this runs. Okay, good. Okay, so this runs. Great. Now let's do the old version with the list. I don't think this will actually make a giant difference because this thing is not very big. This is the one, right? The list one?
Yeah.
Okay, now let's see how long it takes. Ready? No, it's not bad. See, it's going. It takes a while. Good. So it takes a while to process. It might actually overload, which is good. So right, so this is the list version, right? It's building up a giant list right now. Okay, good. All right, so this is actually Illustrator of 1. So 1, you have to wait, and 2, it might like just die because it. This laptop is actually pretty slow. So, but you see the point, right? The list takes forever to build up and such. Then if you actually generator it, if you have it as a generator without the list, then you have it as a generator. Same code, right? Names 4.dat, nothing has changed. Then it just starts running right away. Right? And it starts running, and every time it just a line, it just does. I mean, they're all Bob Smiths, but it just does its thing. Right? So this is actually a pretty powerful illustration. Imagine if you have really big data. So imagine if you had several files to process, and you want to have a pipeline of processing jobs between them. You can hook them with generators. And the cool thing is that in Unix, the pipelines are single. You can't really fork them. I guess you can create named pipes to fork them. Right? You can actually create names that are pipes, and you can actually feed them into multiple. But the standard pipeline is a single stream. So in Python, you can imagine the multiple yields and other parameters is you have one pipeline piece, and then you split it into 2 or 3 different things, and those can independently go. And then you can also merge them later on if you want to be more crazy. So that's a way of doing data flow processing in Python, and it's actually very efficient. So people kind of complain about Python code being very slow and stuff, but actually this kind of analysis in Python is quite fast because your analysis code isn't a lot of code. It's really you're reading from the file, and reading from the file system is a lot slower than executing code in any language. So if you can have compact code that controls reading from files and manipulates that well, your code does actually really fast. So, and with that, let's just go into the interpreter itself because, we'll just briefly go into it. We don't have to do a ton of detail. So, I forgot what our example was. It's .py. So, example is this. Let's kill the counter, and let's just once again look at this counter, just so we can refamiliarize ourselves with it. And now you can see how the code is actually pretty reasonable now, right? That it's basically a while loop, and there's just a yield in the middle. So what this gives you when you compile it when you compile it letters are too small. It actually just makes a function called counter. It just actually makes a function, and then it loads the counter, and then it does the usual setup for loop thing. This is the main for loop. I mean, this is the exact same for loop as if you had an iterator or a list. It's just setup loop, get iter, for iter, so forth. So it turns out we need to actually look inside the function because this is the code for the function. So if we actually do Python it.py, okay, import it.counter. So it.counter is a function. So then we can import this and then disassemble it.counter. So now we're actually looking in the code inside the counter. So this is the counter code. And it's a little long. But the key thing is this yield value right here. That's the new opcode. That's the generator opcode right here. So this means that as you're running the function, it does all its thing. You know, well, we can just trace through it. So it loads low, stores into current, sets up this loop, loads current, compares it to high, cop jump, loads current, yields current, and then the hope is after we are back, we just continue down here, and then we go back up in the loop, and we just keep on looping. So this yield value is the special part, is the special opcode. So if we go to our interpreter, we don't have a ton of time, so go into our interpreter and let's go include, capital I, and then gen object.h. So remember every object has the .h and the include and the .c in the object. So if we look at gen object.h, you should see a ton of these by now. This is the generator object. Pi gen object is a generator object. Again, it starts with an object head, because all objects start with an object head. And then this is the frame. This is the frame of the generator. So remember that after the generator exits, it still needs to keep that frame in scope, right? So remember what the frame is. The frame is this thing, right? So as you execute the generator, you know, it needs to keep this frame. It's low, high, 5, 7, goes again, it exits, and then when you call it again, it needs to like remember that it had a frame. Because the frame died, it got off the stack, but the generator needs to still hold on to it. So I guess conceptually, this generator object has a link to the frame, so that even after my visualization pops the frame off the stack here, the generator still like holds on to it, so that when you recall it, it like remembers where it was. So remember the frames from our like second lecture or whatever. The frames store all your local variable state, right? Your parameters in your local variable state. It's stored in the frame. And a frame is a runtime representation of a particular function call. So it makes sense that the generator object keeps track of its own frame. And then this is, some integer, boolean. Is it true if it's running? I guess, it's false once it's done. Here is the code object. This is the actual piece of code back in the generator that the generator is running. And then this is some weak reference. These are just for garbage collection. But it's three things, right? What's the code? What's my frame? Which includes all the local variables. And am I running or not? And the am I running is, notice when you're done, you should say you stop running so that the interpreter knows to get out of the generator completely or get out of the for loop. It's sort of like the stop iteration exception, right? Which we'll see on your assignment. You need to have a way of getting out. Okay, so that's the PyGen object, and then if you look at objects, capital O, gen object.c, this is just creating generators. So I mean, there's a lot of boilerplate code, and I think I'm trying to find the interesting part here. Blah blah. Send. Yeah, so send is the thing where you can actually send information in the generator if you're curious about for the project. Yeah, so. I mean, if some of you don't have exact project ideas now, it's okay, but we can talk about this in the second half. That there's a ton of interesting things to do for projects. And I think I'm really flexible in terms of and as long as it's interesting enough that kind of sheds light on Python, I think it's fair game. Close, delete. These are all just boilerplate bookkeeping. Throw iter next. Yeah, so the iter next method actually sends something to the generator. So we'll actually see this iter next. Let me keep an eye on this. Get name. Okay, so the gen type. Remember this, everything has a type header, so it knows what to do. So remember how for the iterator, we just call iter next, right? When we do the for loop. Remember how that for loop, you'll see this in the assignment, the for loop opcode will somehow get into iter next. So iter next is here, or TP iter, or iter next is here. So to create an iterator out of the generator object, it calls py object self iter, which I assume is just returns itself. So let's do objects, abstract.c. No, it's not. It's PyObject self-iter. Object.c? Okay, just returns itself. Okay, great. Just some shortcut that just returns itself and increments the reference. So it just says, if you want an iterator, I am my own iterator. And then iterNext is the thing that is called when you start iterating. And in this case, if you happen to be iterating on a generator object, it will call genIterNext every time. So what genIterNext does is it calls genXsend, sendX, with 0 as the parameters. This is the most general function, as you mentioned, so you can actually send parameters in. IterNext just says, we're not going to send anything in, we're just going to call it. So just say 0, so there's an argument instead. So pretend these two are null. This is the generator object, and let's see what it's doing. So it grabs the frame out of myself. So gen is the actual generator myself. It grabs the frame. This is the frame I'm currently running. If it's running, oh, it's already executed. Okay, so this is called, sorry, the first time, because this will actually give you an error if you try to call it twice. So I guess gen_sendX is the first time you run the iterator, sorry, the generator. It happens, so this should be false. So f null, f stack top null. Okay, so that's stop iteration. This is like you have no frame anymore for some reason. Your frame died. Okay, so we pass through these. So you notice how a lot of these interpreter functions start with a lot of error code, right? Error handling, as you see in your assignments. You know, for most part, you just skip over all of them because your code doesn't have errors. And that's why we did not study exception in this class, because I think a lot of it's not super interesting. I mean, it's required if you want to write real code, but so much of the interpreter code is handling errors, because if you imagine in C code, if you don't handle errors, you're just going to segfault and crash. So you have to write so much code to handle the errors and propagate the errors and such, because otherwise you're just going to segfault everywhere. Blah, blah. Another error. Okay, I think this is it finally. Okay, so otherwise there's no argument. Oh, so this is your question about, if we actually send something into the iterator, we actually send an argument in. We can send some data in. If we send data in, then look, what we do is we push the result onto the stack. So it's sort of like we're calling the function again with some extra information. So that's a way of sending new information in a generator each time. So I think the way to do this is actually generator send. I've never actually done this, but I think it's the send method returns the next value or yields it on the send. Generator.send. Okay, so you call it with .send and you send the value. So it goes into the next variable. Oh, interesting. Oh, so next equals, so if you notice this is your 2 yields. It yields, and then it waits for someone to send data in, and when it sends data in, it assigns it to next. And then it yields this next times 2, and then it goes back. So seems crazy. So you can study this code if you want, but it seems crazy. Okay, so that's what the send is. But for regular next, we have nothing. And then what we do is we, oh, perfect. We go to our friend eval frame x. So this is the main interpreter loop, right? This is back in our C eval. So what this does is we set this to running. We are running. Then we just do this. We actually just run its code. We set some state. But really, this is the heart of it, right? The heart of the generator is when we first run it, we actually set its running bit to 1, and then we actually just call eval frame on the frame. We actually just running its code, and then GI running is 0 at the end. So now we're in the generator, we're running it. So now what happens? So now this is the interpreter again. We're running the generator code. So this whatever function was called the very first time we run the generator, and now we're actually in the generator code. So recall that. Sorry, I'm going to go a bit fast here. 10 more minutes. Recall that we need to disassemble the code of the counter itself. So we need to do that. We import it in Python. Import it will import the file and actually run it. So in this case, it runs in x2567. It.counter is a function. So import dis is the disassembler. Dis.dis it.counter will disassemble the bytecode for this. And this looks pretty long because that is that function, right? That's this thing is the bytecode for that, right? Bytecode for that. It's a while loop and the yield right there. So when you call the generator for the first time, it runs this thing, genextend, and then it goes into PyL frame X. It actually executes the code in the generator now, right? So now our interpreter is, yeah, thank goodness you don't have an assignment on this because it's super confusing. So it actually goes inside here and starts executing in the interpreter. So this is all just normal interpretation, right? Normal. All the stuff you've done before, all these opcodes you've seen, except for this one. So let's actually just look at yield value. That's the only special one, right? So we're in the frame of the generator itself, and then we do this magical yield. So let's just continue the story there. Recall in our Python visualizer, what this means is we call the generator. Now we are starting to execute just code normally. It's just normal bytecode execution. And then magically we have this yield, and then something special has to happen with it because it needs to return to the caller and remember something about itself so that when we call it again, it magically remembers where it was. Okay, so we'll spend the last 10 minutes going into the yield value opcode, and then we'll be set, and then that'll be the grand tour. So again, this is PyEval frame X, which is in cval.c, right? This is what we've been looking at every day. This is our giant function. Yeah, this is the giant function because there's a few. So this is the giant function, main interpreter loop. Yeah, you've seen this every assignment, every time. It's giant. Now let's look for the opcode yield value. So there's a ton of comments, but this is basically it. So this pops the return value off. It actually is a return, right? It returns a function. It sets something, and then there's this y yield thing, right? This is, remember how before you were returning out the function as y_return? It's like, why are you returning? Because it's a normal return. Just clean up my frame, kill everything, we're done. Now we actually remember y is y yield. And again, this is just some macro, just some number. So now we go to fast_yield. So in here we stop going through the code. We actually jump to fast yield. So I'm going to search and jump to it, and it's right here. So remember, it's right here, and we're going to jump 1885. We're going to jump down to 2975. So we're here. There's some tracing code, which we don't care about. Tracing is just for debugging, more tracing code. And reset info. Okay, hold on, where were we? It's not tracing, so I guess we reset the execution info. Assert value trace. Okay, so we do some resetting. Okay, what does this do? Reset. This has to do some exception code. Wow. It restores the T state to what they were before the current frame is called. Reset saves them on the frames. Reset can restore them. Can never caught an exception. This is the exception. So this is what happens where, I didn't go into exceptions at all. Okay, this is what happens where you have exceptions kind of pending in your frame, and this kind of resets stuff. So hoping we can gloss over this. Is this all exception stuff? Copy the frame. Yeah, this is all exceptions in the thread state. This is all, wow, okay. So let's pretend like we didn't have to do that. Pretend like our code never is exception, so we don't do that. Then this does, it pops the frame, and it leaves the frame. So now I have to figure out, I saw this in the notes earlier, how does this know how to return back to itself? Why return red values? No. Y yield. So why does this go whole trace by exception? So how does this get back out? It goes y yield, and then it calls. Okay, so I'm trying to figure out for myself how. Okay, so when you yield, it actually is here. It goes back to the value, but when we call it again, it needs to start back at 25, right? So we need to find where it's actually resuming at the next opcode on 25. So I think it's either here or another one. I forgot where it was exactly. I always checked it before. This GI frame. Okay, so if we keep the GI frame around, the reference any longer. GI running, already executing. Huh. That is mysterious. Because I thought in here it would, oh, here we go. CO generate. Okay, got it. Sorry, I'm gonna keep browsing. Owns the rate run the frame. Don't need to keep the reference def back. Is that it? Where is co-generator allow p-call generator? Oh, this is again just tracing code. Sorry, I'm gonna grab generator. Star. No. Alright. There's gen object, object, exceptions, frame object, generator reachable. No, I don't think. Is it in the frame object? No. Sorry, this is kind of mysterious because I swore I saw this before when I was preparing, but I don't see it anymore. This is not relevant. This is not relevant. Oh, compile.c. Oh, when the generator is resumed. Alright, that is mysterious. Okay, I'll have to get back to you on that. Yeah, it's not super clear to me still how the generator keeps coming back because we, the client code, oops, the client code just does a normal for iter, right? Just kind of iterates through it as though it was an iterator. And if you say for iter here, it does the same thing as we do iter next, right? We call iter next. Oh, so it keeps on calling iter next. So it actually, do you think it actually just keeps on calling the generator iter next? Let's just call that. So it keeps calling this, do you think? I think it does, right? But then the problem is that if you call it again, gen_send x 0,
but at that time,
it's running.
That thing's 0, right? It's not running because
the first time you call it's not running, right? Oh, no. Oh, I'm silly. It's always running. Sorry, it's not. It does it, and then it sets it back to 0 again. Sorry, okay.
Yeah,
So this calls it every time. I'm sorry. Okay. And then it saves the frame so that the frame inside of it has the current instruction. Okay, sorry. Now I'm unconfused again. So, sorry, let me explain again. The frame itself, remember this is from like the second class? The frame has the current last instruction right here. Right. Oh no, this is not the last line number. Where is the last? I think it's last I. All right. This is the current instruction it's executing, or the last one it's executing. So if the generator keeps track of that same frame, this number never gets reset. So when it executes again, it just starts off from there again. And the thing I was concerned about is I thought we do running as 1, and then it calls a val frame, and then it never gets back. But actually, right. So when you call this goes and then just goes back to 0, and then just exits. So then when you call iter again, when you call for iter again, every time you go through the for loop, it calls this gen_send x. Every time it calls gen_send x, this thing has already been reset back to 0. So it just keeps calling itself again and again. So it keeps calling itself again and again, and it just keeps track of the frame. The reason why this GI running is 1, which I confused myself, is that if you have this iterator, generate, and you call itself within it, then it will say GI running generator already executing.
Oh.
So I don't know how I can induce this to happen in this code example, but I think you're not allowed to call yourself. Okay, let's pass C into here. This is gonna be crazy. I don't know what this is gonna do. Oh yeah, I can't even do this. So I think if you somehow try to like call yourself inside here, then it will break because you're already inside a generator thing and you try to call yourself again. I don't know how we actually can make this happen, but this plus this equals 1 and equals 0 is just to guard against the case of yourself calling yourself again within yourself. But there is no multi-thread issue. So I mean, another way to think about this is this guards against multiple threads, but it's not a multiple thread issue. It's the issue of inside of your own opcodes, inside the generator, you might be able to call yourself again, and it tries to disallow that. You're like, that's too weird. I don't know what to do with it. So that's basically generators in a nutshell. So in a nutshell, took a while. In a nutshell, it is a very compact way with a yield statement of writing something that iterates, and it's actually quite efficient, right? If we do process, it's actually quite efficient. So if we remember the code for process, it's actually really, really small and compact and really elegant. And the parser function now in our analysis code is still very separated. So I could write the parser and my colleague could write the analysis completely separately. We don't have to know about each other. And when she uses my code, it just magically runs really fast. And if I am naive and I just build up a list, it runs really slowly and runs out of memory. So with that, so good luck finishing the last assignment. We'll see you next Wednesday, right? So next Wednesday we'll discuss this assignment. Cool.